tightrope walker? It seems as if you would need exceptional balance and very sticky feet to walk on a thin rope suspended so high up in the air. Well, good balance would of course be important, but you don't need sticky feet. Tightrope walkers have another secret to help them out, and it's gravity. That's right, they use gravity to their advantage. We can demonstrate this to ourselves by making our own tightrope walker out of a cork, 2 forks, a wooden match without the head, and a piece of string to walk on. Let's take a look at this sketch right here of a tightrope walker. You see this long pole that they're holding in their hands? You notice the ends of the pole sag below the point that they're standing on the wire. Well, the ends of this pole are very heavily weighted, and by virtue of the fact they hang below the wire, they lower the center of gravity of this tightrope walker to a point below the wire. So in effect, he's being held down onto the wire by the heavy pole in his hands. For our very own tightrope walker, take your match and break off the head and throw it away. We don't need the head. You may ask an adult to help you prepare your match. Take your cork and stick the match down into the cork, just like this. You may need to take a nail first and get a little hole to start with, because sometimes the corks are a little tougher than you might think. Now, take the match and carve a V-shaped notch in it with your fingernail in the other end, just like this. Now, take the 2 forks and very carefully insert them in opposite sides of the cork so that they're even, so that they're on both sides and that the handles hang down about the same amount on each side. This takes a little bit of energy. Now test the balance of your tightrope walker. If he's balanced properly, he'll balance on your finger. This one needs a little bit of adjustment. I'd have to adjust the hammer or the handles of the forks so they hang down a little bit better. Here's one I made a little earlier that has pretty good balance. You can see him balancing on my finger. Now we're ready to try him on the tightrope. Take your string, hold one end in your mouth, and balance the tightrope walker right on there. Now, by raising and lowering the ends of the string, we can get our tightrope walker to walk back and forth for us. He uses the same secret of balance that a real tightrope walker does. The weight of the handles lowers the point of balance to a point below the string. Gravity takes over and holds him right onto the string. An amazing feat of balance, and now you know. We'll be back right after this with a more amazing feat of balance. Symmetrical for them to work. Symmetrical means the same on both sides. Our tightrope walker was symmetrical because if you cut him in half, each side of the tightrope walker would be the same. We can do an amazing feat of balance using these 3 unlikely items: a hammer, a ruler, and some twine. Now, how would you arrange these 3 items so that they balanced by a single point? Well, remember our tightrope walker? We discovered that his secret of balance was to lower the center of gravity below the point of suspension. We can do the same thing with our hammer and our ruler. Tie a loop of twine in a small loop about 2 inches across. Slide the loop down over the hammer handle and around the ruler like this. Set it down on the table to get it adjusted so that they all are connected like this. Now, while you're doing this experiment, be very careful of the hammer. You don't want it to drop off and fall on your toes. You need to look around and find a place where there's an overhang, like a kitchen table, that you can hang this whole contraption on. If we've done everything right, our hammer will suspend itself just by the twine and the ruler. This amazing feat of balance is a good one to show your friends. When they ask you how it's done, explain that the center of gravity is below the point of suspension and that gravity is holding them together. A tightrope walker and an amazing hanging hammer, and now you know their secret. Well, next time I see you, we'll explore the law of inertia with a stack of checkers and a ruler, and that's all you'll need. I'll see you then. A line of checkers here organized into 3 sets of 3. How can I change the color of these groups to either all brown or all white? And that doesn't sound like a very difficult question unless we make the rule that you can only touch 1 checker. Now it's a little tougher question, and yet there is an easy answer if you understand the law of inertia. To prove it, we'll need 10 checkers, 6 of one color and 4 of another, and you have to arrange them like this here. 2 dark ones and 1 light one in this group, 2 light ones and 1 dark one in this group, and 2 dark ones and 1 white one in this group. You'll have 1 checker left over to work with. Now, our checkers need to be in a straight line with each of the 3 groups touching each other. So they're touching there and they're touching there. Take your extra checker and put it on the end down here. Get down here where you can see it, line it up, and snap that checker into the line. If you look carefully, what you saw was 1 checker from one group jump to the next group, and 1 from this group jump to this group. This effect, a chain reaction, was caused by the inertia of the first checker striking this group. That action carried through this 2 checkers, and then the end one went into this group. Carried through these 3 checkers, and then one went into this group over here. And finally, the last one was sent away. We can reverse the process and make our 3 groups the same way they were when we started by lining them all up again, making sure they're touching, putting the extra one on this end, and sending them into the group like that. And those are the 3 groups we started with right there. What do you think would happen if we used one checker to set off 2 other checkers? Well, the law of inertia says that the checkers will continue to move in a straight line unless another force comes to act upon them. Well, there is another force acting on them. It's friction. Friction between the checker and the tabletop causes the checkers to slow down quite a bit. If not for friction, we could create an endless chain reaction of checkers. Experiment with your checker chain reaction. See how many different patterns you can create. We'll be back right after this message to try some more checker tricks that are all white ones with one brown one on the bottom. Now, how can I remove this one brown checker without touching the stack and without touching the checkers at all? Here's a hint. You can use a ruler. Well, do you have any ideas now? Well, here's one possible way. By moving the ruler very quickly, you can slice underneath the stack, and the lower checker will move out. Inertia will hold the stack together for just a very brief second, and then it'll drop down. Let's give it a try. Ready? Just like that there. The one checker was removed, and the other ones stayed in line. Here's another experiment you can do with your checkers. Put one white one or one brown one second from the bottom of a group about 6 checkers tall. Now, your challenge is to remove this white one without touching the checker or the stack, using only this extra checker. The rules are the same. The stack has to stay intact, and the checker has to be removed. Do you have any ideas? Well, this one takes a little bit more than inertia. You need a little backspin. This trick also takes a lot of practice. Don't give up if it doesn't work for you right away. I've been practicing all day. I'm going to take this checker right here and snap it downward, backwards. The action of the snap will carry it forward. It'll knock this checker out, and the backspin will cause it to roll away from the stack. Let's give it a try and see what happens, okay? Sooner or later, right there you have it. The law of inertia, and with a little backspin thrown in. Inertia says that a body tends to stay at rest until it is disturbed. And that's what we were doing here, demonstrating the law of inertia today with checkers. Try more experiments for yourself. We can prove the existence of gravity and experiment with weightlessness in our next program. And all you'll need is 2 clothespins and a rubber band. I'll see you then, okay? Are you sure there is such a thing? Do you know how it's measured? Does the moon have gravity? Who discovered gravity? And finally, why doesn't gravity affect astronauts in outer space? Don't be surprised if you couldn't answer all these questions. They've been asked by scientists for hundreds of years, and the answer is just being found today. Let's start with, what is gravity? The answer: gravity is the attraction of 2 large heavenly bodies to one another, like the Earth and the Moon. They're attracted to each other because of gravity. The amount of gravity is determined by the size of the bodies and their distance apart. Well, that's great for planets, but how about you and I? Well, the measurement of gravity upon us is our weight, however many pounds or kilos that we weigh. Sir Isaac Newton, an English scientist who lived during the late 1600s, was the first person to reason out gravity and apply mathematical formulas to it. He predicted that the moon would have 1/6 the gravity of the Earth because it is 1/6 in size. When the astronauts arrived there in 1969, they found out that Newton was correct. If you'd like to know what you weigh on the moon, divide your weight by 6. Let's see, I weigh 72 kilos on Earth, so I would weigh 12 kilos on the moon. Speaking of the moon and space travel, did you ever wonder why astronauts are weightless when they're in outer space? We can demonstrate why this is by using a large rubber band and 2 clothespins. Clip the clothespins on the rubber band like this here, one on the top and one on the bottom, with the bulge in the rubber band in between. Now, you notice that the lower pin stretches the rubber band. Now, to prove that objects are weightless in space, hold the pins above your head and drop them, and watch very carefully when you drop them. As they fall, you notice that the rubber band contracted while they fell. That meant that the lower pin was exerting no pressure or no weight upon the rubber band. It's weightless. Let's look at a picture taken while the clothespins were falling. You notice in this picture that the rubber band has contracted. The lower pin is weightless. This is the same effect that astronauts suffer when they're in outer space. As they fall between gravitational fields in outer space, they become weightless. We'll be back right after this with another experiment in gravity. The law of inertia, which states that an object tends to remain at rest unless some outside force comes to act upon it. This is a pretty tricky experiment, and if you're going to try it at home, you may want to ask one of the adults in your house to help you set it up. For this experiment, you'll need 4 hard-boiled eggs, 4 wide water glasses, 4 paper spools, and a flat, light tray. Fill the glasses about half full with water and set the clear or light tray down on top of it. Place the paper spools directly over the glasses, and very carefully balance 4 eggs on top of the paper spools. Now I'm using hard-boiled eggs here just in case that the eggs decide to move before I get them all set up. Once you get it all set up, the challenge is to remove the tray without disturbing the eggs. If you do it correctly, the eggs will fall harmlessly into the water below. Are you ready for this attempt? And now, for the first time on television anywhere, a demonstration of Newton's third law. Let's give it a try. Just like that. Perhaps you'd like to look at that one on instant replay. You'll notice that as I struck the side of the tray very hard, the tray began to move. The friction between the tray and the spool carried the spools away with it. The eggs were temporarily suspended in space for the briefest moment, then gravity pulled them down into the water. The water absorbed the impact of the eggs falling. Perhaps I'll try it with fresh eggs next time. What do you think? Again, if you'd like to try this at home, ask for help from an adult to help you set it up. Inertia and gravity, 2 important principles of science, and now you know. In our next program, we'll explore music by making our own instruments. And all you'll need are some straws, some wax paper, and a paper tube. I'll see you then.